Hello everyone. This question is from Ampere's Circuital law. It is a part of Class 12 syllabus, and so Class 11 people can leave this as of now. When we discuss electricity magnetism, at that point you can try this question out. So Ampere's Circuital law says that integral of B dot dl over a closed loop, we call that closed loop as an Amperian loop. The symbol is to represent that it is a closed loop. It is equal to mu naught into I enclosed. Okay, the Amperian loop essentially is any closed loop, right? It can be a circle, it can be a square, a rectangle, a pentagon. It should be a closed loop. Okay, and this integral of B dot dl is over a closed loop must be equal to mu naught into I enclosed. Now, if the direction of integral is anti-clockwise, what do you mean by direction of integral? It means the direction in which you move around the loop. So if the direction of integral is anti-clockwise, then the contribution of I enclosed will be positive for the current wires which are dots. Dot means the current is outwards, and so for an outward current wire, the magnetic field lines will also be anti-clockwise. So if you are also moving anti-clockwise, B and dl will be in phase, and so the value of B dot dl will be positive. So please remember, a dot current enclosed will be positive for an anti-clockwise direction of integral, and a cross current carrying wire will have a negative contribution to B dot dl. Why? Because a cross current carrying wire will mean that the magnetic field lines are clockwise, and if you are moving anti-clockwise, they will be out of phase. B and dl will be out of phase, and so the dot product will be a negative value. Right? So that's the expression which we call as the Ampere's Circuital law. What is given over here is an equilateral triangle, which is the closed path over here, or the Amperian loop, so to say, and there are three current wires, and the value of integral B dot dl for wire P is given for the line over the line A to B, and integral B dot dl is given over the line C to A due to the wire Q, due to the current carrying wire Q, which is minus 15 mu naught. I am just assuming this as X and this as minus Y, so that it is easy to calculate this. So now we know that for the line A to B, the wire P has a contribution which is equal to X. We have to find out the contribution of B dot dl over the line AB due to the wire Q and the wire R. We have to do the same for the line C to A, find out the integral B dot dl due to the wire P, Q and R. And again the same for the line B to C. We have to find out integral of B dot dl due to the wire P, Q and R over the line B to C. Now what is given in the problem is integral B dot dl due to the wire P over the line A to B is X, and integral B dot dl due to the wire Q over the line C to A is minus Y. Why minus? Because this is a cross current carrying wire, and so the magnetic field lines will be clockwise, and I am moving anti-clockwise in this loop, and so a negative contribution of I enclosed. Now please realize the position of the wire P is symmetric with respect to the line AB and CA, and so if for the line AB the contribution of the wire P is X, the same contribution of the wire P will be for the line C to A. So integral of B dot dl over the line C to A due to the wire P is also X. Okay. Next, please realize, if the wire Q has a contribution minus Y for the line C to A, the wire P will have a contribution of Y by 3 for the line B to C. Why Y by 3? Because this 3I current is having a contribution minus Y. The negative is because I am moving anti-clockwise, and this current wire is across, but over here the contribution will be positive. For the current wire P on the line B to C, the contribution is positive, and it will be plus of Y by 3. Y by 3 because this will have thrice as much contribution because the current is 3I, whereas the current in the wire P is just I, and so the contribution to B dot dl will be 1/3 over the line B to C. Okay. Next point, for the wire Q, the integral of B dot dl over the line B to C will be x by 3, or will it be 3x? How would we decide that? Just as for the wire I, the contribution over the line B to L, integration of B dot dl over the line A to B is x. This would become 3x. Why 3x? Because this current wire is having a current of 3I, whereas this one only had a current I. So if this current I had a contribution x on the line A to B, the current 3I will have a contribution 3x over the line B to C, but there will be a negative sign as well, because this one is a cross and I am moving anti-clockwise. Okay, so B and DL are in opposite direction, and so you'll have a contribution of minus 3x. Now if I go to the wire R, the contribution of B dot dl over the line B to C for the current wire R, the contribution will be same as Q, because in a way they are symmetrically located with respect to the line BC, so this is also minus 3x. Now moving to the line C to A. We already know the contributions of the wire P and the wire Q over the line C to A. Now for the wire R, the contribution will be 3 times the contribution of the wire P over the line A to B, because I can say that the position of the wire P and the position of the wire R is symmetric for the line C to A, and so this will be thrice as much, but with a negative sign, again for the same reason. This one is a cross, and so the field lines will be clockwise. We are moving anti-clockwise, and so they are out of phase. A negative contribution of B to B dot dl. Coming to the final line A to B. For the line A to B, we already know the integral of B dot dl due to the wire P. Now due to the wire Q, the position is similar as the wire P, but the current is thrice as much, and so this will be 3x, and the current is inwards, and so minus 3x, because we are moving anti-clock and the magnetic field lines of the wire Q is clockwise. Finally, for the wire R, the integral B dot dl for over the line A to B due to the wire R will be thrice the value of integral B dot dl from B to C due to the wire P. Are we clear with this? The wire P has a current I, and the integral B dot dl for B to C is y by 3. For A to B, the current due to the current wire R will have contribution thrice as much. So in a way I can say that integral B dot dl for C to A due to the wire Q, which we have written as minus y, the same value will hold true for integral B dot dl for A to B due to the wire R, because what is Q to the line CA is R to the line AB, and so this will also be minus y. Now using this equation, integral B dot dl is equal to mu naught into I enclosed. I can break it into 3 parts. Integral B dot dl for A to B, B to C, and C to A. And I enclosed over here over the triangle, it will be minus 3i, and plus I. Minus 3i, and plus I. Now over the line A to B, integral B dot dl is minus 2x minus y. Over the line B to C, the integral B dot dl is minus 6x plus y by 3. And integral of B dot dl for line C to A is minus of 4x minus of y. And this should be equal to mu naught into minus 5y. And now we can just simplify this out. We'll get it as minus of 10x minus of 2y plus y by 3, which is minus 5y by 3, is equal to minus of mu naught into 5y. We can simplify this out and we'll get the value of y. Okay, x value is given as 4 mu naught, so this is minus of 40 mu naught. The value of y is 15 mu naught, so this will be minus of 25 mu naught, is equal to minus of mu naught into 5y. And from this we get the desired value of I. You can cancel off 5 mu naught throughout. You'll get this as minus 8 and minus 5, so that is minus 30. Okay, minus and minus is also gone. Okay, you can cancel off the negative signs as well. You get it as 8 and 5, that is 13. Current comes out as 13 amperes, so that's the answer. Okay, it is not a very easy problem on 8 ampere circuital law. You need a certain level of mastery over Ampere's law to understand this concept well. Okay, see you. Happy physicsing.